Hello everyone, welcome you all for the new session on Stereochemistry. In this session, we are going to learn the concept of chirality and symmetry criterion. As a chemist, we are viewing or imagining the molecule in three-dimensional space of great deal. In paper, representing the molecule three-dimensionally is quite interesting. To represent the molecule as three-dimensional object, we need at least one sp3 hybridized carbon atom. Let us consider this stereogenic center which has four different groups in it. So this is a dissymmetric carbon, two-dimensional representation. So if we are drawing it by an ordinary line, then it's of no use. See here, in the second structure represents three-dimensional drawing and helps us to view the molecule three-dimensionally. Normally, we represent the molecule by ordinary lines, which denotes its bonds. However, to represent the bonds three-dimensionally, we use this wedge formula. Here, hydrogen and iodine are lying in the same plane, represented by ordinary lines. Chlorine is represented as a dashed line, which means it goes away from us. Bromine is coming towards us, which is represented in wedged line. Thus, the tetrahedral carbon can be represented by this kind of wedge formula to view the molecule in three-dimensional orientation. As we discussed earlier in our previous video, stereoisomerism is classified as conformational and configurational isomerism. In that, configurational isomerism is further classified as optical and geometrical isomerism. Now, first we will start with optical isomerism. Optical isomers are the compounds, those have same molecular formula but differ in their optical rotation. What is optical activity? So, we know that ordinary lights are composed of rays of different wavelengths vibrating in all directions perpendicular to the path of its propagation. These vibrations can be made to occur in a single plane by passing the ordinary light through a polarizing nickel prism. Such light whose vibrations occur in only one plane is called as plane polarized light. Compounds which rotate the plane polarized light are called as optically active compounds, and this property is known as optical activity. Rotation of plane polarized light can be of two types, dextrorotatory and levorotatory. If compounds that rotate plane polarized light to right, then it is called as dextrorotatory. In Latin, dexter means right. That's why it's called as dextrorotatory. And it is denoted by the letter D or by the symbol plus. Compounds rotates plane polarized light to left is called as levorotatory. In Latin, levus means left. Hence, it is also denoted by the symbol L or with the symbol minus. The change in angle of the plane polarized light is known as optical rotation. The change in the angle of plane of polarization is known as optical rotation. The optical rotation is detected and measured by an instrument called polarimeter. The measurement of optical activity is reported in terms of specific rotation and denoted by the symbol alpha. So, alpha is given by the following equation, that is, specific rotation at particular wavelength and temperature is equal to alpha, that is optical rotation divided by L into C, where L is the length of sample tube in decimeter, C is the concentration in grams per ml. Specific rotation is a constant term at particular temperature and wavelength. Hence, when the concentration increases, observed optical rotation also increases. Using this equation, optical rotation can be calculated for any solution. So, let us first see what is chirality. So, if any object that is not superimposable on its mirror image is said to be chiral. The term chiral is derived from Greek word chir, meaning hand. It is used for those objects which have right-handed or left-handed forms. Molecules which have handedness are termed as chiral compounds. And the property of this handedness is termed as chirality. So the objects which have mirror image relationship and the object and the mirror image are non-superimposable, then it is called as chiral object. Look here, the right hand and the left hand both have mirror image relationship and both are non-superimposable. Thus it is chiral object. Similarly, if we consider pair of gloves, shoes and scissors, they are all chiral objects. By the same time, if you look at the pair of socks or the glass or the ball, they also have mirror image relationship. They are superimposable. Hence, they are achiral. The glass and the ball. So we can imagine symmetry in the molecule. If we can imagine symmetry in the object or molecule like point, axis or plane of symmetry, then they are achiral. The pair of socks, glass, ball, they are achiral because they have symmetry in it. So we can imagine internal plane which will be dividing the object into two halves. This makes the compound achiral. Similarly, when we look at the molecules, so if you consider water molecule, you can imagine a hypothetical plane which will be dividing the molecule into two halves. The object and its mirror image are superimposable. Hence it is achiral. Consider the next molecule, that is CH2BrCl. If you take this molecule and its mirror image, the rotation of the mirror image leads to the object and its mirror image to be superimposable, which results in achirality. Here also we can imagine a plane of symmetry in the molecule. Hence, the molecule becomes achiral. So, the compounds or the molecules, if it has any kind of symmetry in it, whether it is a point of symmetry, axis of symmetry or plane of symmetry, any kind of symmetry will lead to achirality. So hence, carbon atom which has 4 different atoms or groups in it will not have any symmetry. So the tetrahedral carbon with 4 different atoms or groups lose completely its symmetry. Hence it becomes chiral. Look at the next molecule again. So it is represented in Fischer projection formula. Let us discuss about it later. This is chiral molecule. Consider the next molecule. Here also it is substituted with 4 different groups, hence it is chiral. However, these two compounds are achiral because the carbon is attached to identical atom. So here the compound is sp2 hybridized. So that makes the compound to lie on the same plane. Since plane of symmetry is there, so this molecule is achiral. So let us move on to the next concept called stereogenic center. So what is stereogenic center? Consider any chiral molecule. Interchange of any two groups or atoms in it. If it produces a new stereoisomer, then that is called as stereogenic center. This property is called as stereogenicity. Keep it in mind that if we simply rotate the molecule, that will not lead to any new geometry or new molecule or new stereoisomerism. However, interchange of any two groups or atoms, if it produces new isomer, then that is called as stereogenic center. Look here in the next molecule. Here we have taken cis isomer. Interchange of any two groups result in new isomer, that is trans isomer. Hence, this is also called as stereogenic center. So, remember that stereogenic center is not always tetrahedral carbon. So, can be expected in sp2 hybridized carbon also. So, this is called as stereogenic center. So, stereogenic center is not always expected in tetrahedral carbon. As we have discussed earlier, the chiral molecules are those in which the center carbon is bonded directly through 4 different atoms or groups and do not have any kind of symmetry element present in it. And the molecule has non-superimposable mirror image. So they are called as chiral compounds. Let us consider the stereoisomers with 2 chiral centers. So if the molecule has 1 chiral center, we can expect 2 stereoisomers. And in general, if the molecule has n number of chiral centers, then we can expect 2 to the power n number of stereoisomers. This molecule has 2 chiral centers, hence we can expect 4 stereoisomers. Let us take the example of tartaric acid. So tartaric acid has only 3 isomers. We expect 4 stereoisomers for tartaric acid. However, we are getting only 3 stereoisomers. Why so? Because tartaric acid has 2 stereo centers with identical atoms or groups attached to both the stereo centers. Hence, this isomer that is called as mesoisomer. This mesoisomer has plane of symmetry in it. Due to this plane of symmetry, the molecule becomes achiral. So all chiral centers are stereo centers, but all stereo centers are not chiral centers. I have taken tartaric acid example to understand this concept. Okay, let's move on to other molecules which has more than 2 chiral centers. So let us consider this molecule. It has 4 chiral centers in it. So you can expect 2 to the power 4, that is 16 stereoisomers for this compound. However, if we have CHO here and in both the terminals, or CH2OH in both the terminal, then we will not get 16 isomers. We will be getting much lesser than that because there will be symmetry in the molecule. Okay, that is another case. I'll wind up this session with this idea. So we have learned that stereogenic centers are not always tetrahedral carbon, and all stereogenic centers are not chiral centers. Until we meet in the next module, thank you all.